Maybe we get, oh, that's loud. I think it's because it's clipped over here. Well, morning all. My name is John Fernandes. I am a thermal engineer in Facebook's hardware engineering team, and I help Jacob now, who's the lead for the door heat exchanger project, to sort of drive discussions with the community. And today I'd like to provide an update on the specification with regards to some additions that we've made since the global summit, and also talk about harmonization as Jessica brought up during the previous presentation. So the door heat exchanger workstream is one of 3 under ACS, along with cold plate and immersion cooling. And with regards to in-scope activities, since the global summit, we have made a decision to make it open rack compatible only. We will be talking about operating conditions and parameters, whether it's airside conditions or facility liquid conditions. Talk about metrology and performance. What are the parameters of interest? What are the critical parameters? What are some of the target requirements that have been discussed with the community? And we'll also talk about the different types of applications of a door heat exchanger, depending on what sort of cooling do you have in your facility. If you have facility water, you have access to the more traditional approach or a more hybrid approach, as Jessica outlined in her presentation. Or if you have an air-cooled facility, whether it's whether it is airside economized or a more traditional air-cooled facility, you could still use the door heat exchanger to enable some form of advanced cooling. So with regards to an overview of solutions, as I said, depending on whether you have facility water or not, you could tailor your door heat exchanger application based on your requirements. I think most people are familiar with the traditional use case of the door heat exchanger, which is you have access to facility coolant, and your door is responsible for making your rack thermally neutral to the room. And you can choose to be slightly undersized or slightly oversized depending on the application. The other use case, which was outlined by one of our community members, is, well, you have access to facility coolant. Why don't you do even more advanced cooling based on that? So in that case, we could define it as both hot air and liquid to the facility liquid. And then finally, you have an air-cooled facility, but you want to take advantage of, let's say you have a high-density rack and you want to take advantage of the performance of cold plates. Well, in that case, you could maybe drive a closed loop, but still exhaust the heat through the facility air using a door heat exchanger. And over the next few slides, some simple pictorial representations of these different options. So, as I said before, everyone's familiar with the traditional use case. I think over here we're using the terminology traditional solution, wherein you have your door heat exchanger. It could be a passive type where you rely on the fans in the IT gear to drive the airflow through the door heat exchanger and exhaust heat from air to liquid and make your rack thermally neutral to the room. You need to have facility side liquid connections. It's entirely up to the customer whether they want to use a passive type solution or an active type solution. But when we start going over the specifications, specifically in the performance and metrology section, we'll give some guidance with regards to, okay, based on the community, this is the sort of demarcation point at which you may want to consider moving from passive to an active solution. All right. I guess it's directional. The other solution that you could enable based on facility liquid is, as Jessica outlined, is a sort of hybrid solution. And I think with regards to her definitions, this could be a hybrid basic or a hybrid intermediate, wherein you could have cold plates in your IT gear and also use the facility liquid and the door heat exchanger to make your rack thermally neutral to the room. As I said before, we had a community member that outlined this solution that they put together for a customer. If you want to know more about it, you can talk to Cam Turner from Cool IT, sitting in the back there. But the intention here is to, as opposed to having air cooling in the IT gear itself, you have access to facility liquid. You could pump that to your cold plates and enable even higher power components. And what the door does is basically remove the heat from the air from the remaining components that are air cooled. And you may or may not have a CDU. In this case, it's just dependent on how you want to enable this application. And the final solution, which was sort of brought forward as a thought exercise, is, you know, a door heat exchanger has a really large surface area. It's capable of dissipating a lot of heat. Well, that doesn't necessarily mean you cannot apply it if you don't have facility liquid. So if you are looking to do advanced cooling, whether it's using cold plates or some other sort of application in an air-cooled facility, you could still use a door heat exchanger to enable that sort of higher power capability. And over here, you would need an in-rack CDU because we're talking about a closed loop that's driven, a closed loop of coolant that's driven within the rack only. And at the end of the day, similar to an air-cooled solution, you have cold air coming in, hot air going out. All the heat transfer is to facility air only. So here's just a pictorial example to help sort of drive that concept to people's minds. We have a GPU chassis over here that's outfitted with cold plates. So the primary heat exchange for the high power components, in this case, the GPUs in a GPU rack, is the indirect cooling. Actually, you said direct, right?
Direct cold plates.
Yeah, direct cold plate cooling on the GPUs over here. So if I were to go one by one and draw, you know, the connections between the across the entire loop. So the cold plates are responsible for picking up the heat from the GPUs. They in turn connect to the hot manifold. And from the hot manifold, we go to the door heat exchanger, where the air flowing across the heat exchanger, whether it is a passive or an active solution, is responsible for exhausting the heat from the closed loop liquid. That goes to the CDU. The CDU is basically a pump and a reservoir. You don't need a plate heat exchanger in there. But if I draw a sort of analogous comparison to the hybrid solution, in that case you would if you have facility liquid. The CDU then pumps it into the cold manifold, and voila, we complete the loop, and it goes on and on. So this is just a pictorial, a more clearer representation of some of the options we described in previous slides. So with regards to defining the specification, the door heat exchanger group made a decision. We'll define it based on the traditional use case, which is your facility provides you with facility coolant, whether that's a TCS or an FWS. That's basically up to your implementation. And with regards to the specification is divided into different parts. We have the physical, which is the mechanical requirements, loading, what are the interfaces that are required. Then we talk about the data center environment, whether it's airside or facility side. We talk about performance and metrology, and to sort of take a leaf from Jessica's cold plate requirements document, what are the critical parameters? And then what are some of the targets that are recommended for the community? Monitoring and control, we basically define sensors, different types of control, alarms, and also how do we set up the redfish definitions. Serviceability, reliability, and quality, these areas we've been talking about with the community lately. One big question that keeps coming up is how do you do pressure tests, leak detection? How do you ensure that when you're deploying the solution in your facility, you're doing so with high confidence? And finally, environmental and regulations. So with regards to the physical, the general guidance is the door heat exchanger will mount against the rack, and as long as it doesn't violate the sort of outer frame requirements of the door, you're good. And since we have OpenRack V2 and OpenRack V3, there are slight differences with regards to the rack, but the width is still standard 600 millimeters. And with regards to the footprint, the only components that are allowed to violate this requirement are the sort of interfaces that you make, whether that's the coolant with regards to facility liquid coming in, or your electrical and communication interfaces. Also, you could have leveling feet for either load bearing or alignment requirements. That's fine as well. With regards to the depth, our recommendation is you keep this maximum value within 1 foot. We had one of the community members coming to us and saying, hey, our door heat exchanger is slightly more than 305 millimeters. How do we get it in? So to answer that, we also take into account the impact of the door heat exchanger on your facility deployment. Obviously, the preference is to have a hinge solution so that you have access to the rear of the rack for accessibility or servicing needs. And over here, one of the community members said, oh, I can meet 1200 millimeter requirement of the hot aisle spacing. Am I fine? We're like, that's fine. At the end of the day, it's between you and the end user to come to an agreement. With regards to the weight, we have some general requirements. The preferred weight when it's filled with liquid is to be under 100 kilograms. The maximum allowable is 150. This is just based on discussions with the community. And we want the hinge solution to not impact your rack-to-rack pitch or have impact to your data center deployment. So the hinge solution should permit opening of the door by 90 degrees. So if you can meet 2 of these 3 requirements, in general, we could say, yes, your door heat exchanger is good for deployment. And another recommendation is to make it easier for the end user to understand the requirements. We also say, provide the dry weight of the door heat exchanger along with the coolant volume, because at the end of the day, the end user will make a decision based on what type of coolant they want to use, and there are implications of that as well with regards to density. Then the next part of the physical are the interfaces and the connections. This is something that we had a discussion with the DCF community as a part of harmonization, which is, let's say I have a certain capacity and a certain liquid side delta T. What would be the recommendation for the solution side rigid pipe connections? I think that's still in discussion, as a part of harmonization across the different areas. But we sort of solicited feedback from the general community saying, hey, tell us what are the general requirements based on, you guys have deployed solutions at volume. So the general recommendation is we want to make sure that your door heat exchanger solution permits liquid connections, coolant connections from either the top or the bottom. We do not want to talk about the flexible connections that happen between the solution and the facility side. That's up to a discussion between the end user and the vendor. But the general recommendation is for usual applications or the traditional application of a door heat exchanger, we talk about a 1-inch internal diameter BSP type, with the possibility of going to 1.5, but beyond that, it starts becoming really cumbersome with regards to deployment. And under electrical considerations, we have defined some of the AC input requirements. If your rack is set up to have an A and B supply, then the door heat exchanger should comply with that as well. And with regards to AC connections, the agreement is it could be a C14 or a C20 connector. And for communication, either an RS-485 or an RJ-45 with support for Modbus, whether it's RTU, IP, SNMP, or even web server. And a recommendation that was made to us by the DCF community is, since the door heat exchanger supports a given rack, with regards to electrical and communication, the general recommendation is it should be hooked to that same rack. With regards to data center environment, we have some airside conditions that have been outlined. It's very important to note here that we're not talking about the condition of the air that's entering the door heat exchanger. This is the condition of the air that's entering the rack. There may be some amount of preheating depending on what type of end solution you deploy. Of course, over here, we're talking about the traditional solution. So from that aspect, we also defined a delta T requirement which over here is 12.2 degrees C. You could be even more efficient and push 15 or 20 on your IT gear side. But with regards to the 12.2, this could be a good reference point for vendors to define their cooling capacity requirements. Like this is a 20 kW door heat exchanger or a 35 kW door heat exchanger. And that's based on the amount of airflow going through the door with regards to a 12.2 degrees C delta T. So that 12.2 degrees C is definitely a reference point. At the end of the day, it just depends on the IT gear. But we think it's a good reference point to use to define the cooling capacity of the door heat exchanger. With regards to performance and metrology, like I said before, we took a page from Jessica's guidance document and we outlined parameters of importance and units, because if you don't define that, people will either start using SI or they'll start using the imperial units. But with regards to performance and metrology, we definitely want to push for N+1 fan redundancy. Having said that, if you look at traditional door heat exchangers, they use very large fans. And if you have a fan failure, there's the potential to drive recirculation across a closed circuit. So one of the recommendations is to have some sort of impeding mechanism, whether those are just very light louvers or baffles, something along those lines. For the end user who's responsible for integrating the door heat exchanger to the rack, another useful feature is outlining the face area of the door heat exchanger, of the heat exchanger core within the door itself. So they understand, what could be potential back pressure implementations and so on and so forth. And then we talk about airside and liquid side requirements. From an airside standpoint, obviously keep the impedance as low as possible. And as a general reference, the community outlines that if you want to go with a passive solution, then it's important to keep the pressure drop across the door less than 15 pascals at the rated airflow. And if you have an active solution, try to make it as energy efficient as possible. Keep it to under 2% of the rated cooling power. And on the water side, we also define some pressure drop requirements. So across the entire assembled door solution, which includes your connections, your flexible hoses, your sensorics, and so on and so forth, try to keep the pressure drop of the cooling assembly less than 100 kilopascals at the rated coolant flow rate. And with regards to supply pressures, and this is basically feedback from vendors in the community, is keep the nominal supply pressure under 600 kilopascals with the ability to support all the way up to 1,000 kilopascals. And beyond that point, there should be some sort of safety feature that prevents some sort of catastrophic failure. And with regards to monitoring and control, we've been having discussions with the community over the last few months to outline, well, what are the different types of sensors, right? Can we classify them as required or optional? So on the next couple of slides, I'm just outlining some of the sensors that have been defined by the community, whether it's required or optional. With regards to required, air temperature into the door heat exchanger or out. That asterisk means the general preference is to have more than one sensor. Generally, it's 2 or 3. And similarly, for the air differential pressure, we talk about fan speed and a bunch of other parameters in here. With regards to control, this is completely optional. Obviously, with the traditional sort of passive application of the door heat exchanger, it's basically just a dumb door that's responsible for extracting heat from the air coming out of the servers. And it's up to the end user how they want to outfit their solution for their application. But here are a bunch of control parameters and alarms that have been outlined. With regards to reliability and quality, this is really a topic that gained speed after we had the harmonization event with the DCF community. And there were 2 big questions that were brought to the door heat exchanger community. One is, what sort of pressure tests would the manufacturer recommend, or would you recommend to the community to ensure that your solution has been checked thoroughly before deployment? So we worked with the community and came up with a bunch of recommendations. And then the other area was, well, door heat exchangers are kind of notorious for having horrible sealing. So how do we go about fixing that as well? So these are the two main areas that we're trying to follow up on with regards to reliability and quality. With regards to pressure and leak testing, we have divided it into different parts. One is, what sort of checks can you do on the manufacturer side? And then what sort of checks can you do on the integrator or the end user side? And then during application, what are some of the general checks you can do to check for leaks? On the manufacturer side, it changes depending on A, the manufacturer, and B, what the customer wants. But two general reference points that were defined by the community is you do a pressurized nitrogen test at 1.5 times the maximum allowable, which in the previous slide was 1,000 kilopascals. And if you're doing the test for a duration of 40 minutes, then the allowable drop in pressure over that duration is less than 3%. And if you're doing it overnight, keep it under 10%. Checks at the integrator side or the end user are recommended. It could be a similar test, but with just compressed air. If just compressed nitrogen is not available at the integrator side or the end user. Leak detection in operation is either a visual check through the life of the product or using some form of leak detection, whether it's a wire, as Jessica outlined. And with regards to airflow sealing, this is really something that we've reached out to the community to say, okay, what's out there, right? There appears to be an IEC standard that talks about rack sealing or rack airflow containment. So this is definitely a topic that's been in discussion with the community. So here are some of the planned milestones we had outlined after the global summit. We wanted to drive certain sections of the initialized document, and I believe on a lot of these we've had some really good input from the community. Of course, I implore the community to keep attending the calls and driving input to the document so we have a really robust and solid specification. The intention was to have a formal version by this summit, but the last few months we've had so much engagement and input from the community, we've decided to hold off for a little bit, try to get as much of it in as possible, and then release a formal document. And a future goal, as Jessica outlined, is harmonization across the different ACS subgroups, as well as with rack and power and the DCF community. And here are a bunch of the topics. I won't go over that again. I think she's covered it pretty well. And please get involved. So the door heat exchanger community meets on a bi-weekly basis on Thursdays at 9 a.m. PST. Here's a link to the call, and here's a bunch of useful information as well. Please join the mailing list, whether it's the ACS or the door heat exchanger. Please join the other ACS groups lists as well. I think there are a lot of interesting conversations that are happening, and there's a lot of interest that's growing. So yes, please get involved, please contribute. And if I have some time, I'm just going to do a shameless plug. So I talked about the closed loop solution where you use the door heat exchanger in an air-cooled facility. This is something that we've been evaluating with another hyperscaler, and we're looking to initialize a specification or a group based on that, starting with the CDU. I call it a CDU, but it doesn't have a plate heat exchanger. Like I said, it's basically just a pump, a reservoir with filtering and controls. So that's going to happen soon. Please join the door heat exchanger community to exchange emails with either Jacob or I to get involved. Or please feel free to catch me. I'll be here all day today, either at the Facebook booth or walking around. So, thank you. Any questions? Yes?
Do I need a microphone?
Just a question, you were mentioning the sensors that were required.
Yes.
Do you also give a location where those should be placed, or?
With regards to like spatially on the door heat exchanger?
Yes.
We haven't defined that yet. It really depends, right? If you talk about the temperature and the pressure drop measurement, you know, if you ask a vendor, they'll say, oh, 2 sensors are more than enough. Some will say 3 of them
Sure.
are more than enough. And usually the distribution is kind of, if you have 2 sensors, then you do 1/3, 1/3, 1/3. You sort of distribute it equally spatially. But long answer short, no, we haven't defined that yet. But if you think that's
I
that
was
would
just
be
curious
useful.
if you were, at least you know kind of what you're comparing then between different solutions.
That's a
at
good
least
point. I think right now what we're hoping to do is just define and list the sensors so we can get the whole redfish definition started. But we can definitely add more detail as is pertinent.
Sure. Okay. Thank you.
Thank you.